I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on drawing PV diagrams and tying all this together using the ideal gas law, heat, work, internal energy, and the first law of thermodynamics. In this video, we're going to draw PV diagrams and we're going to tie everything together using the ideal gas law, work, heat, internal energy, and the first law of thermodynamics to do calculations for those PV diagrams. So first, let's go ahead and draw a PV diagram. So we're going to start at a position A, and that position A has an initial pressure of P2, and it has an initial volume of V1. And we know that this process is given to us, it's going to be an isobaric process that goes from position A to B and expands to volume V2. So isobaric, we know the pressure is constant, so we're going to draw a horizontal line from A to B. The second process that we're going to draw is an isochoric or isovolumetric process from B to C that decreases the pressure to P1. So we know isochoric means that the volume doesn't change, so it's a vertical line drawn from B to C. And then we're going to have a third process that's an isothermal process from C to A. Well, isothermal means that the temperature doesn't change, so that's going to be a curved graph. So we're going to draw a curved line from C to A, and this encloses the whole cycle A, B, C, A. And remember, you have to draw arrows on your PV diagram so that it's not misread as going the opposite direction in which you want it to go. All right, so we're going to do some calculations on the PV diagram. In this process ABCA, we're going to assume the number of moles is N for the monatomic ideal gas. And the first question is going to be to calculate the temperature for points A, B, and C. So we're going to use the ideal gas law that contains N and R since we know the number of moles, so PV equals nRT. And we're going to rearrange this equation to solve for temperature, so PV divided by nR. We're just doing this symbolically for each of them. You might have numbers to plug in, and then you'd solve numerically. So the temperature at position A, we know that the pressure at point A is P2 and V1 is the volume, so we can calculate the temperature at A to be this value, P2 V1 divided by nR. And then for position B, we use that same equation, and TB is going to equal P2 V2 divided by nR. So that's going to be the temperature at position B. And position B is a warmer temperature or a higher temperature because it's further to the right along that isobaric process. And further to the right means a higher temperature because volume and temperature are a direct relationship. So the temperature at position C, well, we don't have to calculate that because C to A is an isothermal process, which means the temperature doesn't change. So the temperature at position C is going to equal the temperature at position A. So we don't have to calculate anything other than the temperature at positions A and B because C has the same temperature as position A. So we're going to calculate the internal energy at positions A, B, and C. And we have two equations that we could use for internal energy, the 3F's capital N kBT, which we don't know the number of molecules. We do know the temperature from the previous, or we could use 3/2 nRT, which we do know the number of moles, which was given as the lowercase n symbol. So what we're going to do is we're going to use the second one, U equals 3/2 nRT. And again, we're just going to use this symbolically, and I'm just going to use TA, TB, and TC for the symbols for temperature. So the energy at A is 3/2 nRTA, so we can substitute the temperature. Same thing for position B, UB equals 3/2 nRTB. And the energy at C, well, that's just going to equal the internal energy at A because those have the same temperature. So we don't have to calculate the internal energy at position C because it's going to be the same as at position A. So moving on to our next question, we're going to be asked to calculate the work done just for the process from A to B. And remember, to calculate the work done, it matters which direction. And the work is the area under the curve, or we could use work is equal to negative P times the change in volume. Well, we know that the work moving from position A to position B, well, that's the volume expands. So that's going to be a negative work because the gas is pushing the piston out, giving the piston energy from the gas. so it's going to be a negative amount. So work from A to B is going to equal negative P2 times V2 minus V1, and a bigger volume minus a smaller volume is going to be a positive value, and the negative would give us that negative that we would need from an isobaric expansion. So the next question is to calculate the heat transferred for the process from A to B. So we could use Q equals mc delta T. The problem is we know the number of moles of the gas. We don't know the mass. We don't know the molar mass because it doesn't tell us what gas it is. We also don't know the specific heat. So not knowing M and C means that we can't really use this equation Q equals mc delta T. But what we can use is the first law of thermodynamics, delta U equals Q plus W. We know the internal energy at position A and B, so we can find the change, and we already found the work for the process AB, so now we can use that to find Q by just rearranging our equation to solve for Q. Now to find delta U, we just subtract the internal energy at B and A, which would just be subtracting the temperatures, multiplying by 3/2 NR. And we know that the work done, we calculated that in the previous slide, so we're going to subtract that negative amount of work of P2 minus V2 minus V1, and that is going to give us a positive value of work because the change in internal energy is positive, plus a negative is going to give us a positive value, so there's more heat transferred than any of the other two in terms of the change in energy. So Q is going to be a larger positive value than delta U because we're subtracting that negative work. All right, so let's look at another PV diagram. So we're going to go from position A to B, and then B to C, and then C to D, and then D to A. So we have this process A, B, C, D, A. So the process has an n number of moles of gas, and that gas is an ideal monatomic gas. So A to B we know is isobaric, as well as C to D. A to B is a negative amount of work, C to D would be a positive, and B to C and D to A are both isochoric processes, so we know that there's no work done during those processes. So the question is to calculate the heat transferred for the process ABCDA. So again, we could use Q equals mc delta T, but we don't know M and C, so we're going to go straight to our first law of thermodynamics. Delta U equals Q plus W. Now, because the process goes from A all the way around back to A, that means it has the same temperature at position A. So that means delta U is going to be 0. So we can rearrange this equation to solve for Q, and the negative of Q is going to equal W. So all we have to do is calculate the work, and that the opposite sign of the work is going to give us the heat. So we're going to find the total work by finding the work for each process from A to B, from B to C, C to D, and then D back to A. So if we find the work for each individual process, we can add all of them together. So the work from A to B is just going to be the area underneath this curve. But again, that's an isobaric expansion, so that's going to be a negative amount of work. So work A to B is going to be a negative value. Then if we look at the work from B to C, well, there's no area, so that's going to be 0 work that's done from B to C because it's an isochoric process. So from C to D, that's area underneath that is going to be positive. So we're going to add the work from C to D. And then we can look at our fourth process and know that D to A, again, there's no area, so we're adding 0 again. So the total work is just going to be the negative work from A to B, that area, plus the positive amount of work from C to D, which is going to be that total area of that green rectangle, be a negative value. So since work is going to be a negative value, that means heat is going to be a positive value because there's no change in internal energy. So the heat is going to equal a positive value because work is negative. So let's look at some tips that we kind of went through to kind of recap everything that we did in this presentation. So the first thing we did is we talked about calculating temperature. So if you're calculating temperature, we can use one of our ideal gas laws to calculate the temperature at any point, as long as we know the pressure, volume, and number of moles, or pressure, volume, and number of molecules. We can use these two equations to calculate the temperature. Once we know the temperature, then we can move on to calculating internal energy. Now remember that internal energy for a complete cycle, like we saw in the second one, A, B, C, D, A, or an isothermal process, that means the change in internal energy is zero. So there's no calculations that need to be done. We can just know that isothermal along that C to A line in the first one and the full cycle A, B, C, D, A, that means delta U is equal to zero. Or we can use one of these two equations to calculate the internal energy, knowing the temperature using our ideal gas law, or maybe the temperature is given and we don't have to use a two-step process. We can just plug the temperature in. Knowing the number of moles, we'd use the first equation. Using the number of molecules, we'd use the second equation. These two equations give us the value for an individual point. So what we would do then is then subtract 2 points, again, the final position minus the initial position, to find the total change in internal energy. So just between 2 points. So if it asks us to go from A to B to C, we'd just do C to A would be the difference in those. Then work is the area underneath the PV diagram. If the area is positive or the work's positive, that's if the volume decreases. So that's right to left on your PV diagram. If the area is negative or work is negative, that means the volume increases. So that's moving left to right on your PV diagram. We could also use the equation that work is equal to negative P times the change in volume. And then lastly, heat. We didn't really use this equation, but you can, Q equals mc delta T. If we need to know the mass and the specific heat in order to use this equation. But as long as we know two of the three, internal energy, work, and heat, we can always use the first law of thermodynamics. Delta U equals Q plus W. Just rearrange the values to solve for what we're looking for, and you can use these tips to be able to calculate internal energy, work, or heat for any process that you need, so we can find the final third of those. So this is recapping and tying everything all together for our previous videos. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.